So hi, thank you so much. So my talk name is multi-topological fields and NTP2. So I will speak a little bit about fields who has valuation, V topological valuations, and this is a joint work with Sylvain Rideau, who is just there. So I like fields, and I like in particular fields who are kind of similar to the pseudo-algebraic closed fields. So I will maybe remember the definition a little bit. Remember that the pseudo-algebraic algebraic closed fields, they were introduced by Axe in his paper when he tried to describe a little bit the theory of definite fields. And it became really important and one of the main examples for the development of the unstable theories, and that was really a really good field, and a lot of people work with pseudo-algebraic closed fields. Remember that geometric definition if you want. So pseudo-algebraic closed fields is a field that has a lot of points for some particular varieties. So that means that if for every absolutely irreducible variety V defined over the fields, so has a rational point and point in the field, okay? So this notion was really nice, and that was really fruitful, and it was in fact eventually reinterpreted as a special case of a wide range of local global. And we can, in fact, there was a lot of people who tried to generalize this notion for different kind of fields. So we have, I will recall some definition of that later, but so we have, for example, for the ordered fields, we have the pseudo-real closed fields, and for the pedically closed fields, we have the pseudo-pedically closed fields, and also we have ordered generalization, for example, the pseudo-classically closed fields or the regularity closed fields. I will give you some definitions later of that. But my idea is that I will recall you what are our PRC and our PPC fields, because we want to generalize this kind of fields in one only classes of fields, and we want to study the model theoretic properties of these kind of fields, okay? So just to remember, that was the definition that I just give you for pseudo-algebraic closed fields. And pseudo-algebraic closed fields is not ordered, okay? If you want to generalize this notion to have an ordered field, so you need to be a little bit more careful, okay? So what is the definition that gives Prestel for pseudo-real closed fields? So you will not have points for every absolutely irreducible variety, but you will have points for every absolutely irreducible variety that have points in any real closure. So like that, you are sure that you are kind of good with the orders, okay? And you have also the analog for the periodic valuation. So you are rational points if you have points in each periodic closure, okay? So looking at in the orange stuff, I think, yeah. So this is kind of this notion that you don't have points for every absolutely variety, but you have points for every absolutely variety that satisfies something, okay? So this is kind of a geometric definition. What is the model theoretic definition, okay? So to do that, I will just recall you what is a regular extension. Remember that if you have an extension of fields, so a regular extension is an extension of fields who is separable and such that the restriction between the absolute Galois group of n to the absolute Galois group of m is onto. In characteristic 0, if you want to think in that, it's just that n intersection the algebraic closure of m is equal to m, okay? So something important is the absolutely irreducible variety defined over the fields has relation with the regular extension. So in particular, if you have a variety who is absolutely irreducible over the fields, so the field extension between k and k of v is regular, okay? So we can find an equivalent definition, but more in the flavor of model theory for the three classes of field. So how will be an PAC? That will be a field who is existentially closed in the Langenscheidt rings into in every regular field extension. The definition for PRC, it's kind of the same. You are not always existentially closed, but you are existentially closed if you have a regular extension such that you can extend all the orders, all, okay? This is important. This is a totally real extension, an extension such that you can extend all the possible orders to the order field. And you have an analog of this definition for PPC field. So a field is PPC if it is existentially closed, again, respect to the Lancaster rings into each regular totally periodic extension. So that means that you can extend all the periodic valuation as periodic valuation. Okay, so again, so you have this kind of three classes of fields that I like so much, that you have existentially closed in the Lancaster rings if you preserve something, okay? So for example, if you preserve the orders, or if you preserve the periodic valuation, or in the case of pseudo-algebraic fields, you always have existentially closed, okay? So these classes are in fact axiomatizable. It's not completely trivial it's not trivial at all in the Lancaster rings, okay? So what we want? We like these fields, and we want to work in this kind of fields and maybe in other different examples in the same context, okay? It's not new, there were people who did something like that. But the idea is that, so, for example, there is a characterization of, there is a characteristic in these three kind of classes of fields that is true. For example, all these fields are something that is called large, okay? So just to remember, a field is large if for every for every irreducible variety V, if you have Smoid points, so you have, you are Zariski dense in the variety. So you have a lot of points, okay? In particular, all the algebraic closed field, the real closed field, the periodically closed fields are large, but also the PAC, PRC, and PPC are large. So that is kind of a characteristic that we will have if we want to do something with our new classes of theory. So the idea is that we want to define a new classes of theory that we call PTC, that will be we are pseudo T-closed respect to a theory, okay? So that will be the same idea of to generalize the notion that I just did. So you take a language that contains the Lancaster rings, you take a theory that contains the theory of fields, of large fields, and you will take a field in that language, okay? You will write T of K for the models of T that contains K, okay? And we will define this notion of B totally something, or the notion of preserved T, if you want. So the idea is that an extension in general, that will be totality if, maybe I will call it because, to be more clear, so you have an extension is totality. The idea is that we want to preserve this extension, preserve in some way the theory, okay? If for any model of F, for any model of T of K, M, that means M is a model of T that contains K, F, you can embed F in some substructure of M, in some extension of M, okay? Elementary extension of M. And we have the analog for the variety. So a variety is totality if for every model of T that contains T, you have points. The same idea. Remember that for the case of PRC and PPC, the condition was if you have points in any real closure or if you have points in any periodic closure. So that will be if you have points in any model of T that contains K. It's kind of the same idea. So just a little bit looking at the definition of the totality for the case of real closed fields or for the case of periodically closed fields is really be totally real or totally periodic. That means really that you can extend all the possible orders or that you can extend all the possible periodic valuation as periodic valuation, okay? So that really generalizes the notion that we already know for the case of PRC and PPC. So now we will define our favorite class of theories, of fields, well, my favorite in any case, that will be the PTC fields. So it's kind of the natural way to generalize that. So field is PTC if satisfying the following equivalent statements. So any regular totality extension is existentially closed in the Lancaster rings, or for every absolutely irreducible variety totality, that means that any model of T that contains K have points, then you have points, you have rational points in the fields, okay? It's exactly the same definition of PRC and PPC, but now we change totally real or totally periodic for totality, or you change the thing that you have points for any real closure or for any periodic closure to have points in any model of T that contains K. K is fixed, okay?
So the language expands the rings, or it's just ring language? What is the language?
Ring language. And no, L contains the language of rings. It's just a language that contains the language of rings, okay? Later, I will have more specification of the language, but for now, it's just a language that contains the language of rings, okay? Some remark for definition, PTC are large, of course. And this is not completely trivial, but the class of PTC fields is also axiomatizable in the language L, okay? And L, that was the language of the theory T, okay? So this class of theory depends of T, of course, and of the language. Okay, so some examples, of course, if you take the theory ACF, PTC is PAC, well, it's PAC. If you take the theory of real closed fields, PTC are PRC. If you take, and the two first one is kind of clear of the definition, but the third one is not completely obviously. And if you take real closed fields, but with the language of rings with an order, PTC are exactly PRC with exactly one order, so one PRC. One PRC, that means you are PRC, but you only have one order. If you take T as this kind of weird theory, who is real closed fields copies of real closed fields with different symbols for each order, and a model of this theory that will be a model of one of the copies, so PTC will be NPRC. We fix exactly n different orders, okay? This is not trivial, okay? That you need to believe me. You need to believe me a lot of things to do to finish my talk, but in any case, this is true. For the case of periodic fields, it's the same. So you have if you take periodically closed fields, you will have PPC. If you take copies of periodically closed fields with the language that the periodically closed fields eliminates quantifier, you will have also NPPC if you take n different copies. It's kind of the same idea, but now it's not interesting because you have the examples that we already know and that we already know. Really know in the sense of model theory, but we will have new examples too. Okay, the thing is that if you remember the definition, I just put that the fields that the regular extension are existentially closed in the language of rings. So you can maybe ask if you can ask something stronger. So if you can be existentially closed, maybe in the language of the theory T, in a bigger language, okay? In fact, in the case of PAC valued fields, PRC, and PPC, we have something stronger. We already know that. So we have that in particular for the case of NPRC. You are, in fact, existentially closed in the language with the n orders in any regular totality extension. Okay, that was shown by Prestel. Also for the case of PPC, it's the same. You are existentially closed. Okay, this is kind of an abuse of notation, but in the language that you need to have quantifier elimination with the periodic valuation, you are existentially closed in that language too. And for PAC valued fields, that was shown by Kohler, that in fact you are also existentially close in the language with the valuation, okay? If you are just an pseudo-algebraic closed fields with one valuation, so it's fine. So there are three examples that shows that, at least in these cases, you have a stronger property. So we decided to define another class of theory that you can imagine it's kind of related to the fact that you are existentially close in a bigger language, and to try to know if they are the same kind of theory. So the idea is, I will just give you, for now I will change a little bit the notation. I will just take I and finite set. Some of these things that I will say it's true if I is infinite, but in any case. So I will take I infinite, I will take Li for each I, a language that contains the language of rings. And I will suppose that there are only relational language, okay? And I will take Ti and Li theory such that eliminates quantifiers in the language Li. And I will take Li the union of all the language, and I will take Ti the union of the universal part of the theory. So looking at, if I take Ti the theory of real closed field, for example, the universal part only says that you are ordered, okay? So what is the new classes? The new classes of fields that I will define, I will call PIC, peak if you want, okay? So what that means? That you will be regular, if you have a regular extension, that F, so you have KF, a regular extension, such that F, it's a model of Ti. So that means that satisfy the universal part of each Ti. So in particular, again, if you have Ti, for example, the real closed fields, that just means that has n orders, okay? So you are existentially closed, but now in the bigger language, okay? So now we can have a lot of questions, for example, they are the same or not? Or what relation are between PTC and PIC, for example, for a particular theory T, okay? So some examples, for example, if you take Ti copies of real closed fields with different symbols for the orders, so you will obtain NPRC, PIC, that will be NPRC, again for the periodic valuations. If you take, for example, the ACVF as only one theory, you will obtain PAC with one valuation. And in fact, we generalize this a little bit, and we prove that pseudo-algebraic closed fields with n different valuation, it's PIC when you take Ti different copies of ACVF, okay? So now we have more examples, not only PRC and PPC. We have more examples too, that for example, Johnson proved that if you take an K and real closed fields or empirically closed fields or algebraic closed fields and you take different, finally many different valuations, so that will be an PIC if you take the first theory of real closed fields or algebraic closed fields or ACVF and you take the other copies of ACVF in different language. And now we can also play with that because you can have, for example, orders and valuations, and you can take theories that you can take Ti, the complete theory of something who is real closed or who is a Hessian evaluate, and you can take this theory, T, the disjunction union of Ti, and all that. If you have that the topologies are distinct, so you will have also PIC. So we have something that now we can mix, for example, valuation and orders, okay? So now that it's kind of a good notion for fields, but we want to understand a little bit what happened with the more theoretic properties, okay? So of course I don't have any hypothesis of my theory now, so we need to put some hypothesis, okay? I will suppose that for each I, remember that I is finite, I will suppose that for each I, Ti admits a definable Hesselian V topology, and we will call this topology tau I, we will fix it, and we will also suppose something for the definable sets. We will suppose that if you have a model of Ti, so, and you have a definable sets, so Le definable in the model of Ti, then Xi has no empty tau interior in the Mi points of the Zarinsky closure of the set, okay? So we will suppose this supposition, and looking that for we have quantifier elimination in Ti, so the induced topology doesn't change with the model of Ti that I took, okay? So the idea is that maybe I have more topologies, I don't have idea, but I fix one V Hesselian topology for each Ti, and I only have finally many Ti's, okay? And this theorem, who is really, really not trivial, told us the relationship between PIC and PTC, okay? So there are equivalent that K is PIC and the following. But the important thing is that, and I will really speak a little bit about the third condition. So PIC, it's almost equal to PTC when T is this theory, okay? Almost. The important thing is the hypothesis 3, that is a hypothesis that says something about the topologies. This says just that the topologies are different, okay? Okay, you have this second condition who is kind of technical, and we have some condition about density for the definable sets, But this theorem says in some way that the thing that you need to become existentially close respect to a bigger language is to be sure that your topologies are different. Okay? Remember that we have our topologies were V topologies, and in a field that means that comes for evaluation or an order. And so, in fact, there are really, the fact of B or be existentially close for a bigger language, they're really related with the topologies. Okay? So, now we understand what happened, what is the relationship between PIC and PTC, and we want to study a little bit model theoretic properties of that. I will just recall you really quickly that, for example, in PRC and PPC we have this theorem. If you are a PRC or a PPC fields, you are dense in the real closure or in the p-adic closure, for example. So maybe we want something similar for some kind of closure for us. And also different orders or different p-adic evaluation in the two cases are induce different topologies. So I will take some notation. I will fix PIC, okay? K. I will choose some model of Ti that contains K, and I will take Ki, Li, the model of Ti, intersection with the separable closure of L, okay? We have quantifier elimination, so I really don't care about what model I take. And for every V topology on K, because remember that I fixed one topology for each I, but maybe I have more, in particular in V, because the topology was in Ti, okay? So for any V topology in K, I will define this set, E tau, that will be the set of Ki such that tau I induce tau in K, or with the union of the separable closure of K. And we will say that a set Ki here is minimal if for any other elements in the set, Kg, so any embedding of Kg to Ki is surjective, okay? The minimal elements exist, and this will be our closure in some way, because we obtain that if you have a V topology in K, and you take the minimal element of this set, so you will be dense, okay? That will be our tau closure in some way, okay? Also, there is a nice result who are true also in PRC and in PPC. That was shown by Jardin and Fred Jardin for PRC and Fred Jardin for PPC. The idea is that, you know, if you have V topology, something who is really nice is true, you can take one open in each topology, and you can take the intersection of all open, and that will be always different to the empty set. This is really strong. But this is stronger, because that says that you can take a smooth point in some variety for each real or p-adic closure, and you can find a rational point in the field who is close to all the points that I take it. Okay? It's kind of stronger. And we want something similar for our case, and we obtain the same for our closure. So that means that if you are PIC, you take the minimal element for E tau I, so our closure for the theory, for the topology tau I. If you take an absolutely irreducible variety defined over the fields, you take open in the Ki, inside the variety but in Ki. So you can find a point who is inside all the intersection of the open and in the field, and in the variety of rational point, okay? So it's exactly the same theory. So now we want to understand, for example, what happened. We want to understand what happened, for example, if each Ti is in TP2. So, for example, PIC will be in TP2, or if we can or not know the burden of the theorem of a PIC field. If you know the burden of the Ti, for example, there's this kind of theorem we want to prove. So this is what we know about PRC and PPC. So what we know that for the case of PRC, PPC, or PAC bounded fields, where bounded, that means that you have a small Galois group, or for any n you have finally many extensions of degree n, so you don't have a lot of extension. So for that case, we have that that was proved by Zoe for one direction and Zoe and Anand for the other, that if M is PAC, so M is bounded if and only if the complete theory is sample. Also, that was proved in my thesis for PRC, the same idea. If you are PRC, so you are bounded if and only if you are in NTP2. And also, for the case of PPC, that was also proved in my thesis, only one direction. If you are PPC bounded, so the complete theory is in NTP2. So we have some relation, and we want to know what can we do for our PIC fields. Okay, so now we will work in PAC bounded, because of course we want to be bounded to try to do something. So we can suppose that we have a language that has a lot of constants because we want to encode a little bit the algebraic extension. So I will fix my perfect bounded PIC field. I take a language that has a lot of extension, and I will also fix a model of Ti that contains K. Okay? So with that, we can prove, in fact, something who is a little bit more general than the theorem that I just showed you. It's kind of approximation theorem for types that says that, in fact, the same is true for PRC and PPC. So they say that if you have F, algebraic closed inside K, and you have V, an irreducible variety defined over F, you take P and type generic inside the variety, and you take now an open set who is consistent with the I part of P, okay? So you take your tip in the big language, and you take the reduct of this tip for the language Li, and now you take opens inside the variety, and you know the hypothesis is that you know that the opens are consistent with the I part of P for each I. So it's true that you can find, so that what we obtain, that P, the old type with all the language, is consistent with the intersection of all the open sets. Okay? So it's more stronger than the other one, and this is really, really important for everything. It's kind of an approximate theorem for types that works really, really good. With that, we obtain, for example, we want to understand definable sets. Of course, we don't have quantifier elimination, but we obtain something similar to the thing that we already know in PRC and PPC, something that we call density theorem. That means that even if you don't have quantifier elimination, you are really similar, when I say really similar, I will call you what that means, but you are really similar to quantifier free definable sets, okay? So I don't want to let you all the theorems, so by the idea, I will just put everything together, and the idea is, so you have your definable set, definable with all the language, okay? And with some parameters. So you can find, for each I, you can find finally many Yig for some G smaller than some M. So finally, in any case, and another definable set that will be just small, such that satisfy the following. So the idea is, all these for each I, all the Yig is open, okay? And definable with the same parameters. And also the definable, the dimension of the order set, it's small. And also you have density of the set in any element of this union. And you don't have equality here, but you have that X is inside that. So X is really kind of similar in some way quantifier free definable sets. It's not equal, but it's dense, okay? And so the proof of that, in fact, it's fine if you have the order theorem. So it's kind of quickly if you have the approximation theorem for types, okay? And I really, really think that you don't want to listen to all this theorem, but I just put that. What is the idea of the amalgamation theorem? So maybe you can just ignore all the technical hypothesis, but the idea inside that is that, okay, you want to amalgamate types. Usually you cannot. You have a lot of things, but you can, in some way, if you can amalgamate quantifier-free types. Okay? This is the idea of the proof. The same theorem is true for PRC and for PPC, and that was made in my thesis. And this is a generalization of that, and the proof is a really Galois theory proof. Okay? But the idea is that, because looking at where I am saying, so I have this element, these tuples in K. I take the algebraic closure of each of the AG and take CG that enumerates the algebraic closure of F of CG. Okay? Well, I assume something that is not important. And the idea is that you're looking at C1 and C2 has the same type over F. Okay? But only over F. Okay? But you know that there exists C who is independent of everyone who have the same quantifier free type of each CG for each AG who is the algebraic closure of something bigger than F. Okay? So in that case, you can amalgamate this type though. So you take the type of C1 over A1 who is bigger than F, because this is the algebraic closure of FA1, with the type of C2 over E2, and you cannot change the quantifier free type of C over A1 and A2. So, in any case, the idea is that if you can in some way amalgamate quantifier free types, more or less, you can amalgamate types. Okay? And with this theorem, with these two theorems, we prove something that Sivan called the magic theorem, or the magical theorem, because that really works everywhere. What is the theorem? So suppose that you have an A inside K, algebraic closed. You take X, a quantifier free set, definable over some parameters and non-empty, okay? And you will take a formula with parameters in A, okay? And you will take AG with G and omega in discernible sequence over A, okay? So the idea is, if you have that for one of the elements of the sequence, you are dense inside X, so you will find an element who satisfies all the phi, okay? And this is really useful. So what happens if you put together this result, to prove this result, you really need the amalgamation theorem, and you really need the density theorem, and I don't know why I decided to do this sketch, but I will do it. So the idea is that, so of course we will use Erdos, Rado, and stuff like that, so I want to extend my sequence via some big cardinal. I will be enumerate for each G finite subset of kappa, finite, I will enumerate the algebraic closure of AG, okay? In a good way. Who is good with inclusions, there is the idea, okay? And then, in fact, this is not a sketch, it's a sketch of the sketch, if you want. Okay, so you will find, in a magical way, an element C who will be algebraic independent of all the elements of the sequence, okay? And such that the type of AG for all finite G inside omega only depends of the size of G, okay? But we only find this G independent of everyone such that the type over AC depends on the size of omega, but we don't know anything about the formula. Okay, remember that we want to prove that we have an element that satisfies all the formulas. We don't know anything about the formula now. So this is some technical. We suppose that we can suppose that if you are two disjoint set, you can suppose that the enumeration is only the intersection of the two enumeration is only A, because we want to use amalgamation theorem. So this is why we need to suppose that. Okay, and now this is in fact this is just compactness, if you want. So now you can find another C that will be, you use the order C to find this C, so it's different C, but you use the first one to find the second one, such that C that will be algebraic independent of all the AG. Also, the quantifier free type only depends of the size of G, but the most important thing is that this C satisfies the formula, okay? So, and then it's almost finished because we just use amalgamation a lot of times, and you have, and compactness, and we obtain that the intersection of the formulas are in fact consistent. This is why I told you that in fact it's a sketch of a sketch. You need to believe me a lot of things, but this is the idea. But the important thing that you can remember here is that the important is to know that amalgamation the magic lemma are really crucial for this part. Okay. So if we want to study, I have how much time to be? Oh, fine. So if we want to study the burden of PIC fields in terms of the burden of TI, well, we want to do that. So just to remember what is the burden, I will just recall you what is an impattern. So it's kind of, if you know what is an NTP2 theory, it's kind of the same idea, but here you can have different formulas and you can have different inconsistencies. And just to remember you, an impattern of deep kappa in some definable sets, that will be a set of formulas, phi L, so L that will be indexed by kappa, and remember that the depth is kappa. So a set of definable subset phi L of M A L G, so L that will be indexed by kappa and G over omega, such that, so the idea is, so you have different formulas for each line, so how many lines you have, so you have kappa, and you have KL inconsistent in each line, so the KL that can be different in each line if you want, but you will have consistent in each path, okay? The same idea is of NTP2 if you want. The burden of a set that will be greater or equal to kappa if you can find any pattern of depth kappa in the set, and you can define, if you want, the burden as the sub of the kappa such that the burden of the set is bigger than kappa, okay? So, and in theory, I forget, a theory is kind of strong if there is no impattern of infinite depth in models. So, now I just recall you what was a PIC in case you forget it, because I will tell you what is the relationship now between PIC and the burden of TI and the burden of our PIC, okay? So just in case you just forget, remember that we have n different theories in a language that extends the language of rings relationally, so we don't have functions. This is important. And you take Li, the union of the language, and you take Ti, the union of the universal part, and remember that a field is PIC if for any regular extension such that F it's a model of the universal part of each Ti, so you are Li existentially closed, okay? Just in case you forget it. Sorry, I know that there is kind of a lot of definition here, so I try that you recall a little bit what I'm talking about. So the idea is that this is the theorem that we have. So if you have, so suppose that you have NTI and the burden BDNI, that will be the burden computed in terms of the theory TI of some K fixed PIC, perfect PIC bounded field. So the idea is that we know now that the burden that will be the burden of the set, or any set, that will be bounded for the addition of, what do I want to say? If the burden of x for each I is smaller than kappa I, so the burden of x is smaller than the addition of the kappa I, okay, who was expected, okay? And in fact, if the equality is strict, so you have also that the equality is strict. And of course, that implies immediately then if you have, for example, that each TI is in NTP2, of course, you will obtain then PIC that will be also in NTP2, okay? So to prove this, it's not complicated. You do that by contradiction. You suppose that this is not true. You take your impattern who will be bigger than the addition of the kappa I, and you really use, again, the magical lemma to reduce the problem to one line and to find, in fact, consistent for one particular line. So it's kind of the same idea. It's kind of the same idea, again, using the magical lemma everywhere. And But you need to do that, you really need the lemma, the other lemma to have a contradiction. Okay, so maybe you can also ask me if we know something different for the other direction. We're thinking that was the easy part of the proof, in fact. Because, if you know that you have an set such that the burden is bigger than kappa I, so you will have an in pattern, and it's kind of clear that the burden for each I, that if you put all together, that will be kind of clear for us that you will have an burden and in pattern bigger. But in fact, that was kind of complicated, and then takes us a lot of time. Just quickly, I will not really give you the sketch of that, but the idea is, so you assume, well, you can assume that you are in the affine space, so you can suppose density, you use density to suppose that, in fact, your set will be tau dense. Tau is the topology that comes for all the tau topology, remember? And remember that you fix it, tau e for each I. And so X will be dense in some intersection of Xi, where Xi is definable and tau open. So we prove that we can suppose that. Also, if you suppose things, and this is the tricky part. In fact, this is the problem, because the in pattern that you find for each Ti have parameters, maybe not in K. That will have parameters in Ti, and to have parameters in K, that was complicated. we didn't arrive for a lot of time. But now we prove that, in fact, we can find any pattern such that these sets are, in fact, opens, and that the parameters are in K. And now it's fine, because in the moment that you know that you have a lot of in pattern and a lot of in patterns with parameters in this set, you can just put all together, because you have consistent for each I, but there are opens, and you have V topologies, so intersection of open sets in different V topology that will be always different to the empty set. So the idea that we take for any path an open set for any path for each I, and we take the intersection of everything, and that will be an in pattern. Of course, the inconsistent, it's clear because we didn't change. But all that together, that will give us an in pattern of depth, the addition of the kappa. So we obtain that, in fact, for every perfect PIC field, so the burden of a set who has dimension D, that will be the addition of the burden for each I. So it's fine. So that gives us a corollary, who is kind of nice, because we already proved, and that is something that you believe me, because it's not really easier, but we proved that a perfect pact with different end topology is PIC. So that implies, in particular, that, so the theorem before implies that, in particular, if you have IPIC perfect and bounded with VI and independent non-trivial valuations, so the burden of K with the valuation will be N. Okay? So now we kind of understand, in the sense of the universal shallow, if you want, where is the pack and valued fields. Also, we can think about, for example, what relation is between, I don't know, forking in each Ti or dividing in each Ti with forking or dividing in T. Why not? So as you can imagine, if you have a type that do not divide over A, this is equivalent to the type do not divide over A for all I. Okay? So division, that will be, not division if you want, that will be equivalent to not division in each Ti. So it's really related to the division in the theories Ti. Again, this is the same idea. So the theory T or the theory PIC, it's really related, the characterization, the characters that we know are really related with the characters that we already know in each Ti in some way. And in particular, if you are an extension base of Ti, then of Ti for all I, so A will be an extension base of K. So of course, if forking equals dividing in TI, so you will have that not forking, it's equivalent to, in our PIC, to not forking in all I. So it's the same idea. So forking and dividing are really, really related of what happened with forking and dividing in each TI, even if we don't have quantifier elimination, and you know that these definable sets are different and everything, but really only everything depends of the topologies in the end, and everything depends of what we know about this topology in each TI. Okay? So I think I will finish here. Thank you.
Any questions? Me? You have a question?
So may I ask, so let's say if you know that if of each of the TI is model complete or like strongly model complete, do we know that the overall theory is model complete too?
If you yeah.
We do. And maybe just a second question. So just now you only have less than equal, but don't you have the equality in the burden?
Where?
So is that
Now here we obtain the equality. Yeah. So I just did before one direction and the other direction, but in the end we obtain the equality for the case of bounded, yeah.
Any other questions? So
It's somewhere there.
So what's the paper of Collard that you mentioned?
So the paper of Collard, he shows in particular that, in fact, it's a small paper, I think, it's kind of 11 page, that shows that if you have a PAC fields with evaluations, or you will be existentially close in regular extension. In the regular extent that you can extend the evaluation.
Yes,
no,
but what's the geometric statement that he proved exactly?
Yeah, it's true. It's proved the geometric statement more.
And is this also true for finitely many independent valuations? Like, again, if you have finitely many independent valuations?
Collard only do that for one valuation, yeah.
Yes, but I mean, do we know if it's true also?
Yeah, we prove for any.
We
prove. So Collard say that for one valuation, and we prove for any, for finally many valuations,
Yeah,
so for
probably
n different valuations, yeah.
any other? So Sami, what about forking if forking is not equal dividing? I mean, you said.
What about
forking? You said it in the remark, right?
So the remark says that if in TI.
Yeah. But if it's not, I mean, in general.
I don't know. Yeah. This is like, yeah. When you have the parameters upside, it's kind of messy to be sure to have the good parameters in the field. So yeah, I don't know.
Okay, let's thank Sami again.